And at the edges, you reappear on the other side. You can never fall off. And furthermore, it's orientable. Now this seems like fun. We actually built something from multiplication, so let's try it again. How about we multiplied a circle times a two-dimensional sphere? Circle times a sphere. Circle is one dimension, the sphere is two dimensions, so we're going to get a three-manifold from this structure. So what does this mean? At every point in my sphere, that's sitting in my sphere, I need to associate to it an entire circle of possibilities. But remember, we cannot have these circles intersect as we put it on the sphere. So we do the same trick we did before. We take each one of my circles, I cut it open and I make it into an interval, but remember the identification for the two edges. I take my sphere, I stick my intervals on there, and I do this for every point on my sphere. And if I do this, you get a hairy-looking ball. But if I do this for every point that you can imagine, you actually get a thickened sphere, where the inside shell and the outside shell of this thickened sphere are identified. Why? Because this interval really was a circle. These 2 points were identified, which means the inside shell and the outside shell are identified, which looks something like this. Now again, we have another three-manifold. Notice that this object is finite. You can hold it in your hand, it's orientable, and it has no boundary. When you come to the outer boundary, you reappear on the inside because it's coming from that circle property. So what are some other properties of this circle times a sphere? Well, we can take a spherical slice of this object, and when we do this, notice we have an entire circle's worth of spherical slices. You can slice it here spherically or here spherically. In fact, you have an entire circle of possibilities, which makes sense because this is a circle times a sphere. But surprisingly, we can also slice it horizontally. And when I do this horizontal slice, notice that you get an annulus. You get a disc with a hole in it. But the inside circle of the annulus and the outside circle of the annulus are the same because they're glued from the circle gluing property. And when this happens, notice if I take an annulus and glue the inside and the outside, I get a torus. So we're actually getting a two-dimensional torus sitting inside this three-dimensional world. Things are far from obvious, even in this simple world. But what about knots in this world? Remember knot theory, the idea of knots we studied in 3 dimensions? Well, what if you put the knots in this three-dimensional world? It turns out that there are at least 2 kinds of unknots in this world. Here's an unknot, just a plain circle that's just floating on the side. This is what we're completely familiar with, but here's another unknot. It goes from the bottom part of the sphere to the top part of the sphere. Remember, they're glued together. And having 2 kinds of unknots feels like we'll have 2 kinds of knot theory. Indeed, we can tie knots that go from the top with a knot structure inside and that glues to the bottom, which again, by identification, is a perfect circle that's knotted up. But look at this amazing property. If I have a crossing that's really close to the interior sphere, I can pull that strand under that sphere and loop it all the way around so the crossing now becomes the other side. I've changed an overcrossing into an undercrossing. And by doing this repeatedly for any knots, it turns out that all of these knots that come from this top to bottom structure can be untangled. Thus, there are different kinds of knots here. And the knot theory in this 3-manifold is not like classical knot theory at all. It becomes far more difficult, and we have to be careful about subtleties. 3-manifolds are complicated objects. Now, let's look at one more 3-manifold, the 3-dimensional sphere. Remember, to draw the surface of this 2-manifold,
Alright, that was all I believe that covered what I wanted to talk about. That was a topological sphere within a sphere with strings attached, strings or knots attached, and that's what my invisibility is all about. I was inspired from my low-tech applications, or from my low to high-tech applications, and then onto a cosmic application. This is one of my only a concentrated intersection of reality can combine the flat geometry of our universe with that of the hyperbolic geometry of the ADS-CFT. Correspondence there is an invisible as well as a holographic bound, and that's what I found on the internet, which resembles the outside in the inside of one of my typical drawings, diagrams, and this is a holographic bound and the invisible bound. I was inspired by Landauer's principle of the conservation of information, but I took that and extended it to space and all the information inside space. You're not making an object invisible, you're making the space that the object rests in invisible. And as you've seen with the video that was just shown, wherever something disappears on the outside, it reappears on the inside because those boundaries are connected. Well, I've had this idea for a long time that leads to stuff like portals, even artificial portals, and by this is another picture of it, the invisible bound, the holographic bound. Wherever space itself disappears, it must reappear somewhere else. And this is another picture. Wherever space disappears in one space-time, or whatever, it must reappear somewhere else in another space-time. And combine that to my, I called them APROs at one time, but I now call them artificial alternate reality orbs, to encompass both parallel and serious realities. And this is artificial portal, invisibility wrapped around a holodeck. As you can see, those are the strings that combine the outer shell to the inner shell, and as a standalone holodeck, and they could have a dual correspondence between another holodeck somewhere else. I know these two environments look too familiar, too similar to really show the contrast. And there are low-tech APROs, which I now call AROs or AROs, artificial alternate reality orbs. They used to be alternate parallel reality orbs. There's photographic, there's televisual, and there's the bridged horizons of realities that can only be achieved, I believe, with solving the ghost interfacing paradox. This is the ghost interfacing paradox. I believe in order for a portal to be real, it must exist totally outside of our reality, visually and physically, invisible and intangible to light and matter. This is a tall order, but what's even greater is the scenario of two or more twin portals in the same realm of reality. Portals, to be real, must pass through all reality and each other like ghosts. A true portal must be undetectable by anything in our reality, rule 1, while being able to detect so as to pass through and manipulate everything in our reality, rule 2. If a portal can detect another portal, it is breaking rule 1. If a portal can't detect another portal, it is breaking rule 2. This is the ghost interfacing paradox. And this shows a picture of orbs passing through each other in an ideal ghost interfacing in our reality. And I believe metamaterials might be a periphery in visibility, and light field, my light field interface concept could be both combined together to create something more likely to produce a portal. I'm not interested in programming the universe, as is the title of a recently famous book by an MIT computer quantum engineer. I'd just like to compute a patch of the universe about the size big enough to build a portal. Quantumly compute just a patch of the universe. So these are my ideas. Thanks a lot for watching, and I hope you see where they're supported by the video that I just posted, just showed. Thanks a lot. Bye.